Hello all, it's lovely to see you.
Hello.
Yeah, yeah, what a week. Yeah.
Are we going to go over hydrolysis of amides?
Well, we haven't really talked too much about amides yet, but
Oh,
we
that's
will.
what I see.
Okay.
Okay,
Yes.
yeah, I got to that problem and I was like, yeah.
So
no.
what I'm hoping today is for us to finish up the last few details of chapter 17 and then talk about the part of chapter 18 that isn't the neurotransmitters part, just like what are amines, how do we classify them, and then there's a little bit of chemistry with them, but very little.
Okay, now I'm just curious, what is the correct way to say that? Amides or amides?
Amides.
Okay.
What is going on? Yeah, amides. A-M-I-D-E-S, amides. Some people that I respect pronounce them amides, but that's one that there's a little bit of leeway. Amide or amide, either one of them is fine.
To spell it and then pronounce it makes it sound like it's phonetic, which it's not.
Right.
Yeah.
So we've already talked about the formation of esters from carboxylic acid plus alcohol. All right. So the general form of that reaction looks like this, where if we have a carboxylic acid with alkyl group number 1 here, plus an alcohol with alkyl group number 2, if we put those together using an acid catalyst, we get an ester where the alkyl group from the alcohol ends up attached to that oxygen part that's attached to the carbonyl, and then also water. Now, here's the key thing, all right? You can get 2 for 1 with this reaction if you remember it this way, because this is an equilibrium reaction, which means that if we want to make an ester from a carboxylic acid, we put an excess of alcohol in there to push the reaction to the right and make ester. If we want to hydrolyze our ester, in other words, if we want to take an ester and turn it back into a carboxylic acid, we use the same catalyst, but instead we treat with water. Because this reaction can go in either direction, putting water in can push us back to the carboxylic acid. Does that make sense to everybody? So it turns out, and I don't know, honestly, I can't remember if your book discusses this, but the catalyst that can be used can be an acidic or a basic catalyst. Now, in terms of catalysis, I don't know if this fits the definition of catalyst because I think you do actually use up some base in the reaction, but we can use acid or base to turn our alcohol and carboxylic acid into an ester. We can also use acid or base to turn our ester back into a carboxylic acid. So one place that you might have seen this reaction before is in the hydrolysis of triglycerides. And although we could do this with acid or base, it's much more commonly done by adding a base in. We call this saponification. So we can do water and an acid, or we can do a strong base in water like sodium hydroxide. So hydrolysis of an ester in base is what we call saponification. This is a way to make soap. So for example, the strong base, pioneers might have gotten this from using lye as their source of strong base. And then their triglycerides would have come from animal fats. So animal fat and lye together give us a carboxylic acid. And in basic conditions, we also know that carboxylic acids lose their protons. So imagine that all three of these long fatty acid side chains are the same length. I tried to make them that way. In basic conditions, if we were doing the reaction that way, we would end up with 3 of those carboxylates. And then the other part here, a 3-carbon triol called glycerol. So the important part out of that saponification is those carboxylates, that very long fatty tail and a very polar ionized head group. This is what we call a detergent molecule. So detergent molecules are really, really good at dissolving greasy dirt because they can surround that dirt with their non-polar tails and then can interact with water with their ionized head. All right. So anytime we have, well, detergent, we could in general call this some sort of a lipid. Anytime we have a polar head group and a non-polar tail, we're talking about some kind of a lipid. All right. But that is an example, like probably the best example of hydrolysis of an ester. So we can see that this isn't just any old ester, it is a triester. There are 3 ester functional groups in there, and we hydrolyze all 3 of them to get our carboxylic acid back. Because I've shown this in basic conditions, we know that in basic conditions, we also are going to take that proton away from the carboxylic acid. So let's talk about a very similar set of reactions, all right? So last time we learned how to form an ester and how to hydrolyze an ester. Today we're going to learn how to form an amide and how to hydrolyze an amide. And I'll be the first to admit that the book's way of talking about forming amides is not the most common way that chemists really do this reaction, all right? So let's say that we have a carboxylic acid. We could treat this carboxylic acid with any of NH3 or NH2 with 1 alkyl group attached to the nitrogen, or NH with 2 alkyl groups attached to the nitrogen. So based on the fact that we know we have to have a full octet any one of those ways, we know that each of these can form a bond using that pair of electrons to our carbonyl group here. So these are all reactions that give water as one of the 2 products. Where is my phone and why is it yelling at me? So imagine that we put together ammonia, NH3, and our carboxylic acid. If we take out the OH group from the carboxylic acid and one of those 3 hydrogens, that gives us water as one of our products. And the other of the products is an amide. So remember that amides can be primary. This is a primary amide because it has exactly 1 bond from nitrogen to carbon. Or if we used an amine like this with 1 alkyl group attached to it, so that's a primary amine because that nitrogen has 1 carbon attached to it. Then we end up with a secondary amide. Secondary because the nitrogen has 1, 2 carbons attached to it. If we start with a secondary amine, so that nitrogen having 2 alkyl groups attached to it already, and combine it with a carboxylic acid, we end up with a tertiary amide. So tertiary amides are a little bit different because note now that nitrogen has 1, 2, 3 alkyl groups attached to it. It does not have any hydrogens covalently bound to it anymore. So primary amides and secondary amides can hydrogen bond because they have hydrogen, at least 1 hydrogen, covalently attached to that nitrogen. Tertiary amides cannot hydrogen bond, at least not with themselves.
So when you said they can hydrogen bond, you specifically mean they can hydrogen bond themselves as
Yes,
well as other
that's
things?
the,
Okay.
That's the first thing that you always think about when you say that thing's capable of hydrogen bonding. Like it can make a hydrogen bond with another molecule of the same thing. So if we have
Okay.
2 of those together, they can hydrogen bond with each other. Now, there are some molecules, and this tertiary amide is one of them, that because there's an electronegative nitrogen and an electronegative oxygen, if we have another molecule around, like water, for example, that is capable of hydrogen bonding because it has one of those special hydrogens, then in that case, this tertiary amide could form hydrogen bonds with water, but water would have to be the one that donated that special hydrogen for the hydrogen bond. So when I just say they can hydrogen bond or they can't, I mean with themselves, all right? And in all of these cases, the way that we put the carboxylic acid together with whatever amine we're talking about, the book's method for doing that is heat. You heat the 2 of them together. It works, it's slow, the yields are not very good for these kinds of reactions, but the reality is that this is the simplest way of explaining how to make an amide from a carboxylic acid. Any of the other ways that I would teach you how to do that take more than 1 reaction, so they're a little bit too much for us to remember at this point in our chemistry lives. So if you want to learn some of the more awesome ways that chemists learned how or have learned how to turn carboxylic acids into amides, pop into my office hours and I'll show you some really neat ones because there are a bunch. This is a reaction that chemists find very, very useful because formation of amides is one of the ways that chemists can link amino acids together to make peptide chains. All right, and synthetic peptides are really important molecules in terms of the drug world. So being able to form amide bonds like this, a bond between an amine and what was a carboxylic acid over here, those kinds of bonds are some of the most important bonds that we learn how to form in organic chemistry. But for right now, if we put the amine and a carboxylic acid together, we get an amide and a molecule of water. So whenever we make a molecule of water from a reaction, that is an example of a kind of reaction what we call a condensation. A reaction that produces water is a condensation. So all these reactions are condensations. Now, in the opposite direction, getting our amine and our carboxylic acid back from an amide is very much like what we do to do hydrolysis of an ester. So hydrolysis of amides can work in either acid or base conditions. If we treat that amide with either an acid or a base, we're going to separate our amine and our carboxylic acid from one another. So what amine and what carboxylic acid did we put together here? Well, before that NH2 had a bond to that carbonyl, it had one more hydrogen attached to it. All right. So let's talk about the products of this reaction if we do this reaction in acid. Because honestly, the products between these two ways of doing it are a little different. And we'll talk about why. This is actually also an excellent bridge into the amines chapter. So imagine when we break our amine and our carboxylic acid apart, there's our amine. Well, in this case, just ammonia. There's our carboxylic acid. But we have to think about what this reagent, the acid or the base, can do to these products. So here's the first time where I'm going to tell you that amines are basic, which means that they can pick up H plus from acids. Now, if we have a lot of HCl, a strong acid in this solution, that means that this is not going to be the likeliest form we're going to find our amine in after the reaction is finished. Because the conditions are acidic, instead, that amine will have picked up an extra H plus and become NH4 plus instead. So let's think about the same kind of reaction, but instead now, we're going to do the reaction in basic conditions. Remember that hydroxide, OH minus, is a very strong base. So when we split those two apart, when we do the hydrolysis reaction, we get our carboxylic acid and our amine back again, but we have to think about what that strong base can do to either of these products. Do we know anything about what strong bases do to carboxylic acids? We learned about that last time we were together, which was like close to a week ago at this point. Monday. It was really close to a week ago. Monday. Strong bases can deprotonate carboxylic acids. They can steal this H plus away. So when we do a hydrolysis of amides in strong base conditions like this, instead of getting the acid, the carboxylic acid and the amine back in this form, the carboxylic acid comes back to us without its H plus. It comes back as a carboxylate instead. So anytime we see a carboxylic acid in basic conditions, we should write it without its H plus as a carboxylate instead. So very, very similar to the reverse reaction for what we did for an ester, right? We can hydrolyze, split an ester back apart into an acid and an alcohol. with acid or base conditions. But when we do this same reaction with amides, we have to be really careful because no matter what reagent we treat with, whether it's acidic or basic, one of those two products is going to be affected by that, because acids will cause the amine to pick up an extra proton. Bases will cause the carboxylic acid to lose a proton.
And
if you're working through the back of the chapter problems and you did some of the amide hydrolysis reactions, that's when you'll see sometimes a carboxylate show up. And in the back of the book, they might show this with the Na plus along with it, like the Na plus counter ion right next door. I don't care if you write that in there, because in an aqueous solution, those two ions are not paired anyway. They're separate from one another floating around in the solution. But if you want to write that counter ion, that's totally fine. Here, if you wrote the NH4 plus as your product, you could write Cl minus as the counter ion along with it from the HCl, but who cares? All right. I just want you to show that that amine has picked up an extra proton because of the acidic conditions. So let's do another one of these together where our amide is not your amide anymore. Juan, it's all right. My phone is going off the hook and going crazy too today. I finally threw it because it was irritating me. It can go like 2 hours and I don't get a single notification, and then as soon as I start class, it's freaking blowing up. So,
I had to mute while my phone was going off.
Well, that's kind of a gross picture. I'm going to draw that again just because I don't like the way it looks. Hashtag OCD. All right, that's much better. So that is a tertiary amide. What are the products going to look like if we hydrolyze that amide in acidic conditions? So let's say H2SO4, strong acid conditions. And what about if we use potassium hydroxide, strongly basic conditions? You get the same two products. You always get your carboxylic acid and your amine back. They're just going to look a little different because of the acidic or basic conditions. So see if you can find the two products here. First, acidic conditions. When we break that bond between the carbonyl and the nitrogen, we're going to give our acid its OH group back. And we're also going to give that nitrogen a proton back to turn it into an amine. But what happens to this amine in acidic conditions? The final product isn't the amine, but instead that amine is going to use its pair of electrons to pick up one more H plus. To make an ammonium ion. In other words, amines end up carrying an extra H plus and are positively charged in acidic conditions. So this and this are the correct two products of our amide hydrolysis in acidic conditions. This normally requires heat to, or at least a very long reaction time.
For that reaction, since the acid is H2SO4, I see where the H2s go in the reaction. The SO4, does it become SO3 as an acid?
Well, since the H2SO4 has lost one proton, it becomes HSO4 minus. So HSO4 minus you could think of as the counter ion to the N plus here.
I guess I'm wondering, where does the hydroxy group come from? Because it come from the water?
From water. Yep, from water.
So it's H2SO4 in water solution,
Yes.
and the water breaks down in the acid solution to get OH.
Yes, that's right. So in reality, no matter what strong acid you're using here, the real thing that's giving the H plus away is H3O plus, because any strong acid that we put into water is going to give its protons away to water first to make H3O plus. If we were to use a strong base like sodium carbonate instead, really no different from a hydroxide base, because carbonate is a strong enough base to take protons away from water to form hydroxide. So these are both examples of strong bases, but any strong base that you put into water, you're going to end up making hydroxide ion.
Okay, so you can kind of think of it as two reactions then, where you have your amide plus you have your acid plus water, and the acid in the water makes H3O positive.
You can if you want to. That's just, you can think of this as like 4 different reactions together. So we can think about how the acid reacts with water. We can think about how the H3O plus reacts with this stuff along with water to break this bond. We can think about what happens to this in the H3O plus after. So in the end, I just want you to know that acidic or basic conditions will split our amide back apart into a carboxylic acid and an amine. You just have to be careful in acidic conditions to know that that amine is going to be carrying an extra proton. All right, that's the easy way. In the end, you always know you're going to have your carboxylic acid and your amine back again. You just have to check and make sure that they're in the right protonation state based on whether you're in acidic or basic conditions. So in basic conditions, we get the same 2 products back, but in basic conditions, carboxylic acids don't have their proton anymore. They are deprotonated. And amines are not protonated, they are neutral in basic conditions. So that's why it's really important for us to understand that carboxylic acids are acidic functional groups. In other words, they give their protons away in basic conditions. It's also important for us to remember that amines are basic functional groups, which means that in acidic conditions, they will pick up protons. So that's the way that we get to the right answer when we're talking about hydrolysis of amides.
Okay. Thank you.
And to be perfectly honest, like that's pretty much all I wanted to cover in terms of what amine chemistry we're going to learn about. Amines are basic. They pick up protons in acidic conditions. That's the big reaction of just amines that we need to know about for chapter 18. Other than that, most of what we're going to talk about for amines is going to be like half a lecture next week where we talk a little bit about neurotransmitters.
So for this portion, we do need to know like the full reaction, not just one part of the product. We need to know all the products of it, not
Well,
just
both
like
of these products are organic products. They
Okay.
both have carbony parts to them, right? So let's do a couple of examples where there are no R's, where we see everything to make sure that we understand like how that works.
I'm confused.
So here is our amide. Still not particularly impressed with my ability to replicate molecular geometry here, but whatever, close enough. Let's say that we are hydrolyzing that amide in sodium carbonate. Remember, sodium carbonate is strongly basic solution. And any of these conditions where we're hydrolyzing, when I say sodium carbonate, I should be more specific and put AQ afterwards so that we know we're talking about in water also. So Ariana had a really good point. Where the crap does that OH group come from to give its carboxylic acid back its OH? If you don't see any extra H's around here, it comes from water. So it's important reactions are done in water, which is why they're called hydrolysis reactions.
Besides being a charged ester, is there another term for it?
What?
Besides being a charged ester, as
What's a charged ester? I don't know what that is. An ester doesn't have a charge. So an ester looks like this. We could talk about like the ester version of this. Instead of, if this is an amide, here's what an ester would look like that has a similar structure.
So would this be?
So give me the two products of hydrolysis of that ester in strongly basic conditions.
OH.
Think about what bond you're breaking here. In each case, whether you're talking about an ester or an amide, the key bond that we're breaking when we do hydrolysis is the bond between the carbonyl and that other atom that's next door to it that's not carbon. So this bond here is the one that we're going to be breaking. This bond here is the one that we're going to be breaking to get our carboxylic acid and our either amine or alcohol back.
Huh.
So we have to think, after we give this thing its OH group back attached to that carbonyl, what is that going to look like in strongly basic conditions? Instead of having an OH group, we are likely to have that carboxylic acid deprotonated. In other words, we're going to have it as its carboxylate instead. Our other product, the amine, will be given back one proton, which is enough to make it a neutral amine. So note that that secondary amide, so the nitrogen is attached to 2 carbons. When it gets hydrolyzed, the amine that comes out is a primary amine because the nitrogen is attached to 1 carbon. And in basic conditions, when we break apart our ester into a carboxylic acid and an alcohol, our alcohol gets its proton back, but our carboxylic acid, which is an acidic functional group, in other words, gives its proton away, we write it as the carboxylate in basic conditions.
So that I guess that was my question by saying charged ester, and I knew that wasn't right. So that's considered a carboxylic acid still.
Yes, it's a carboxylic acid, but just a carboxylic acid at a pH where it doesn't currently have its proton. So call it a carboxylate, but it's still, the functional group is still there. It just doesn't have its proton right now. And as a matter of fact, most of the time in neutral aqueous solutions, carboxylic acids look like this. They don't have their protons at pH 7.
So the difference between an ester and a carboxylic acid missing its proton is the fact that that oxygen has 2 electrons extra.
The difference is that esters have an alkyl group attached to that oxygen. That's an ester right there. It has an oxygen with an alkyl group attached to it.
Okay.
Dr. Musk, where's that second hydrogen coming onto the nitrogen on that first one?
Where does that come from?
Yeah.
From water. So when I
From the
say
aqueous solution,
that means that in all these reactions, there's plenty of water floating around, and that's where the extra H's come from.
okay.
Yeah. So I can show you how this reaction works. It is a complete pain in the keister to write the full mechanism out, and it's not something that I want you guys to remember all of anyway. But if you really want to know where all the protons come from and where they go, I can show you that. That's one of those things that old crusty organic chemists have to have memorized.
I was just confused on where that second hydrogen was coming from.
Yep. So
You know,
remember that these reactions are aqueous. They're done in water. So
Okay.
that's where the extra hydrogens are coming from. And honestly, the extra oxygen here comes from a water as well.
Okay.
for that NH2, you know to add an extra one so that when the amine is by itself, it has the right number of valence everything, which would be 5.
Which would be 8 valence electrons.
Not valence electrons. So I always count up to 5, sorry, for nitrogen. You make sure that it matches up, right? That's
Yes.
how you know to add a hydrogen.
Yep. We know that in general, amines that are neutral have 1 lone pair and 3 bonds. So if we only have 1 alkyl group bound to that nitrogen, then in the end, that nitrogen has to have 2 hydrogens and a lone pair, because nitrogens have 3 bonds and a lone pair. That's their normal way of behaving in organic molecules.
Yeah.
So now that we know that acidic conditions can turn an amine into something with a positive charge, we call that positive thing an ammonium ion. Let's do one more of these hydrolysis reactions, and then I'm going to talk to you about how we can use acid-base extraction to isolate amines the same way we can carboxylic acids. And that'll be the last thing that we're going to talk about. I don't want to go more than an hour today because I know it's Friday night. You guys are tired. I'm tired.
3-day weekend too.
Which is awesome. That will be great because I can spend all weekend getting Canvas caught up for you guys and for my other class, because this week I haven't been able to do squat.
Was chapter 17 homework going to be pushed a day or more because the video is not being available?
I think I already did push the due date for it, if you check it out. If not, then yeah, obviously you'll have enough time after I post the videos to get that done, okay? Yep, I am not in the business of trying to squeeze you guys to get homework done super fast when I haven't got content up yet. You can start out as a first principle that I will be fair with you, and you can argue if you don't feel like it's actually happening that way. And I will be, I'll listen, I promise. So let's talk about this amide. I don't know why that bond is drawn so long. I just can't draw anything right today. So let's say we are hydrolyzing this amide in acidic conditions. Just using nitric acid, another strong acid. What would we expect the two products to look like? Are we supposed to get like white death tonight?
Yeah, 3 days of snow.
3 days of snow?
Well, I'm in Bellingham, so I don't know if our stuff's different up here, but yeah, 3 days.
You guys will probably get a lot more snow than us because you've got some elevation and you're more inland.
Yeah, I live up on a hill at the top of a cul-de-sac. So literally that difference of like 30 feet. We can't leave our house, even though everybody else can. So it'll be interesting.
Better go to Winco and stock up now while you can.
No, if you live in Bellingham, you don't go to Winco.
I don't know where you go if you live in Bellingham.
Yes, you do. Winco's great to get your shelf items and canned goods.
Trader Joe's.
Last
Trader
time
Joe's? Is there a Trader Joe's in Bellingham?
Yeah.
there was a line out of Winco that wrapped around the building the last time I tried to go.
Or if you're getting salsa, Trader Jose.
No.
Fair. Am I muted? Nope.
Like, I'm not gonna lie, but without having the videos, I feel like I'm drowning.
Marlena, I promise I'll have the videos so you can catch up, okay? So we're doing things backwards. We're doing a little bit of recitation now where I haven't got all the videos posted. Like once you have both the recitations to look back over and the topical videos, hopefully it'll be easier. So for now, at least you still have the PowerPoints that you can look through. But when you look through I know, PowerPoints with commentary and annotations are much, much better. So I'm working on it. I just I think it was Tuesday, my computer almost went to the graveyard. So I did some sort of a password and security update and applied the settings that SVC wanted me to apply, and then nothing worked anymore. So I have been trying to conduct most of my business via a phone for the rest of the week, which is horrific.
I have a question.
I might have an answer.
When we're looking at our reactant there, is there a way for us to know whether it's acidic or basic by looking at it without you telling us?
So if it's an acid, it's going to be one of a short list of strong acids that you should remember from Chem 121, like HCl or HBr or HNO3 or H2SO4 or HI. So that's basically it for really strong acids. And then anytime you see something like group 1 metal with OH minus, anytime you see hydroxide, it's some kind of a base. So hydroxides are all basic ionic compounds. And the only other strong base that I could think of that you'd be likely to see, because it happens to show up in the homework assignment, is like a carbonate base instead. So really, those are the kinds of bases that we would normally use for this hydrolysis reaction. And something like this would be the acids.
So the HNO is an acid. You keep telling me what we're using and then I forget before I can do the problem.
Yeah, HNO3 is what we're using right now. I was just giving you examples of both, like so that you can write down these are the different acids that you might see. These are some bases that you might see.
Okay. So everything above that line is an acid at this
Yes.
type. I like that. I'm gonna mute this.
Is it pretty much if there's an H in it, it's going to be an acid because that makes it acidic? And if it has an OH, it's probably going to be a base?
If it has hydroxide ions in it, it's going to be basic. Having H's in it doesn't necessarily mean it's acidic. What about NH3? NH3 has 3 H's in it, and that's not an acid. It's actually very strong. It's pretty strongly basic. So we just have to remember that when we put H's with any of the halogens other than F, those are very, very strong acids. And then here are a couple of other very strong acids. These are just like really common sources of strong acid that chemists use all the time. So it's sort of if you don't remember that, go back to Chem 121 and look over our little list of strong acids. Those are the ones that I make students remember from 121.
My teacher didn't make us memorize those. She was just like,
I barely remember what I did on my last class last quarter, let alone a year and a half ago.
I know. But that's why I'm willing to talk through the list with you again, instead of just like showing you one and another, and then which ones do I know? And then you see a different one on the test and you're like, what the hell? Yeah. So there's the short list of strong acids that are pretty common. There are a bunch of other ones, but if I look in my cupboards at the lab, I'm probably pulling one of these things out if I need to use a strong acid. If I need to use a strong base, I'm probably pulling out either potassium hydroxide or sodium hydroxide.
If you put one on the test that wasn't discussed, I'm going to text you with daggers.
Well, you know I'm going to do it now just on purpose, out of principle. What if I put lithium hydroxide instead? You couldn't figure that out? The hydroxide ion's still in there.
I would still send you daggers.
And now I got to do it.
Stumped.
is it the
Okay.
disassociation energy that differentiate an acid from a base at all?
So I don't want to talk about dissociation energy. That's probably not the best way to think about this. The best way to think about this is,
That's how my last teacher talked about it, and it didn't make a lot of sense.
that's why it's a bad way to talk about it.
Okay.
Yeah, it's not a good way to talk about it. We can talk about
Let's just not.
Never mind. Probably
yeah, let's not for now. Okay. So in terms of evaluating what makes a good acid and what makes a good base, that's actually something that we start to talk about in the third quarter of the 160 series. And you keep on talking about all the way through majors level organic chemistry. So thinking about what makes H pluses likely to be stolen, in other words, what makes an acid, because acids give away H pluses, what makes a base, what makes a molecule likely to pick up an H plus, it's pretty complex. So for example, what is it about that alcohol that makes it not very willing to give away its H plus? Because obviously it is much less acidic than the carboxylic acid is, right? The alcohol kept its proton, the carboxylic acid lost its proton. What's the difference between that oxygen and that oxygen that one keeps its proton and one loses its proton? Take the majors level organic class and find out.
Cliffhanger.
Yeah, I know. It's too much. I'm trying to spare you guys the level of detail that would be required to know that. All right. It's really complex. There's actually an acronym associated with how we quantify how strong acids are in organic chemistry. And it's an acronym because, with an acronym with 4 letters, because there are 4 different things that we have to consider about a molecule to decide how acidic it is. It's a lot. It's a lot. So we're not going to do that in this class.
Okay.
Love it.
Need
All
more
right.
time.
So right now, we're talking about doing hydrolysis of an amide in acidic conditions. Remember that the amide bond, the bond between the carbonyl and the nitrogen, that's the bond that breaks. And in acidic conditions, let's evaluate what we expect of our carboxylic acid first. In acidic conditions, conditions where there are lots of H pluses around, we would expect that our carboxylic acid keeps its proton. In acidic conditions, conditions where we would expect lots of H pluses around, we would also expect our amine to pick up an extra proton. So it's going to pick up a proton anyway because it needs 3 bonds in a lone pair to be a neutral compound. But in acidic conditions, it can pick up an extra proton and become an NH3 plus instead of just an NH2.
I was taught to draw them as an electron pair with the hydrogen just next to the electron pair. Does it matter if we draw it as a bond, or should we
Draw it as a bond. It's a bond. It's a covalent bond, just like the other bonds.
Okay.
So if you want to shorthand it and just say NH3 plus, and then that's totally fine. But every one of those 3 bonds between nitrogen and hydrogen are identical to one another. There's nothing special about that extra H that gets picked up. We have 3 identical bonds between nitrogen and hydrogen there.
Am I going to be marked down on homework if I already turned it in and didn't do that?
No, it's fine.
Okay, thank goodness. I didn't want to redo my homework again. Okay.
I mean, you're still showing the pair of electrons being shared, but I'm just telling you there's nothing special about that shared pair compared to the others. They're all identical.
Does it give off its proton easier?
Yes. As a matter of fact, ammonium ions are acidic, which means that if I put this in with a base, it's likely to give one of those H pluses away. What is an acid? At least the Bronsted definition of an acid is something that can give away its proton to something else, right? So whereas an amine like this is not likely to give away another one of those H's, and ammonium, where that nitrogen has a plus charge, any hydrogens that it has, like that first one, is going to be pretty easy to give away. So ammonium ions are acidic functional groups.
Okay. That's when my last teacher taught us that way. She wanted us to do the 2 electrons to denote the fact that that hydrogen, while it's bonded, is easily taken away.
All right, I suppose I can. I mean, I don't like it, but I accept it.
Okay.
Are these getting added like the first 2?
Well, what?
Are these getting added like you had in the first 2 equations?
Yeah, those are both those 2 products.
Okay.
So I just didn't write the plus sign, but yes, both those 2 things are the products of the reaction. So if you look here, the difference between what we have here and here, in order to make the equation balance out atom-wise, we actually have to put in an extra water in there. Is that right? Actually, we have to put in an extra water and an H plus. So it looks like we add 2 hydrogens to our amine and another hydrogen to the carboxylic acid. So 3 total hydrogens have been added. I don't worry that much about atom balancing my equations in these reactions, because with water in the equation, we can give or pick up H pluses at will. All right. If we need an extra oxygen, that can come from water also.
So
It's a lot easier to not try and atom balance everything for these reactions. It's confusing.
in the book, it talks about it forming ammonium salts, and it does the whole
So
Brackets.
if you want to make an ammonium salt, then that positive ion has to have a negative ion along with it. A salt is an ionic compound with a positive ion and a negative ion. So what salt would we be forming here if we had used HNO3 for our reaction? We'd have that ammonium ion with a plus charge, and then our counter ion, our negative ion, would be the nitrate ion.
So would the correct answer of like the products to that would be a carboxylic acid plus an ammonium salt of ammonium and
The correct answer here is these two products. And if you want to put the counter ion for that ammonium compound, then you can. But because this is aqueous, those two ions are not paired up right now anyway. They're floating around separate in water. So I don't care about the counter ion here. Notice here, I could have written the counter ion K plus along with it. If that makes sense to you and it makes you happy, do it. That's perfectly fine. But in aqueous solution, these two ions are not going to be directly paired up anyway. So that's why I don't care too much about writing the counter ion to this positive ion or the counter ion to that negative ion. It's just not the important part of the product.
That's because in aqueous, the lattice structure is disintegrated. Is that right?
Ions are separated and surrounded by solvent water molecules. So these are not directly paired up in aqueous solution. They're just floating around in the water.
The book doesn't do a great job explaining that second part.
Yeah, I know.
It just says, and then there's ammonium salt.
Yeah, where did that extra ion come from? So I suppose if the book is like really caring about balancing the equation atom-wise, and they're considering balancing the equation charge-wise, then having the counter ions in there is important to balance charge. But in reality, it's in aqueous solution. We can have charged things in aqueous solution. It's fine. All right, we're at an hour, folks. So I will be updating a lot this weekend. I'll have at least chapter 17 and probably 18 out as well. I'll have reading quizzes. I will have labs, and I'll make up a schedule so that you'll have plenty of time to do those things. We don't have class on Monday, which I regret a little bit because I'm gonna miss you guys, but it'll give us a couple days of time to sort of work through 17 and 18 since we haven't had those topical videos updated in a while.
Thank you.
Yeah, somebody chatted in. Well, you're welcome, Candace. Okay, everybody have.
Practice test will be up like midweek.
What?
Oh, will the practice test be up like midweek? Maybe like Wednesday?
As soon as I get done with chapter 17 and 18 content, then the next thing that's on the list is the practice test.
Okay.
Oh,
So as soon as I can, but it'll be up next week sometime for sure. And if we have to take a couple of extra days before we take our second exam, I'm cool with that too. It's totally fine. We'll get through it.
What day is our exam potentially supposed to be?
I don't remember off the top of my head.
It was supposed to be the 22nd.
It says
Okay.
the 24th now.
Oh,
The
it does.
24th.
Yeah.
So I think I did that. I think I did that to make the exam day a Friday, so that way we wouldn't lose a day in class together for exam day. And if it needs to be a little bit beyond that, then that's totally fine. It's fine. Any other questions? I know that this is really confusing, but just think like individually, when you have a carboxylic acid as a product of a reaction, think about what it's going to look like depending on whether the reaction was acidic or basic. If you have an amine that is a product of a reaction, think about what it's going to look like
That one.
acid or base. What? Can you guys hear me?
We can hear you. I think it's Emma's internet's freaking.
Yeah. Emma, your internet connection seems like it's about to die.
I'm back. Everything was black and I couldn't hear anything.
We can sort of make out the words that you're saying.
I'm like a transformer.
Yeah. But we're pretty much done anyway, so I'll get videos posted as soon as I can, and then Orlina, you'll have both sets of data to pull from as you're starting to like make sense of 17. 18 is not really that hard. The important part of 18 is what we covered today about amines, that amines are basic functional groups that they can pick up H pluses. All right. Also, it turns out that amines happen to show up in lots of important biological compounds. So the amines chapter is the chapter that the author decided to use as sort of the bridge into the more biochemical part of the textbook. So we talk about some neurotransmitters. We'll do that for 20 minutes or so next time we're together on Wednesday.
Definitely going to use all your office hours next week.
Sweet. Have a wonderful weekend, everybody. Enjoy that extra day and make sure that you have plenty of heat and food for the snow death that's coming over the next few days.
How much snow are you guys expecting? That I'm
Armageddon.
again?
On Whidbey, it's going to be like a dusting, I'm sure. So
okay.
I'm from the Midwest. If we get a foot of snow, I'm going to be outside like making snow angels in shorts and a t-shirt.
I'm trying to expect what I'm flying back to.
Yeah.
Well, like,
are you coming back soon?
On the 26th, I fly back to Washington.
A couple weeks. I bet you by that time all the snow is going to be gone. You know, it never sticks around for that long here anyway.
It's like 2 or 3 days max usually.
Yeah.
But
all
the
right,
last
everybody. I gotta get going. So have a wonderful weekend.
Thank you.
Yeah.